Earlier, this HF linear board of VU2EVQ design had a short when I had tried to set the bias for IRFP 150 MOSFETs. So now I am checking whether there is any short before testing. That is by checking the positive and negative power supply lines to see if it is shorted, keeping the multimeter in 200 ohms range. No short is seen. As during the previous test, I am testing with the 9-volt battery for a safety concern. With the small 9-volt battery connected and the range in 20 volts DC, that's DC range with a straight line and 3 dots over there, and this is AC range. So I am testing in DC range and checking the voltage of the battery now. Let us see. The battery is 8.93 volts, a little below the 9-volt rating. Here is the initial test of the probably idle current, keeping the range in 200 milliampere, and I am testing the drain of the whole board. Current drain of the whole board, it is around 15.8, 15.7 milliamperes for the whole board at 9-volt supply voltage. So that is reasonable. Next, the bias can be adjusted by turning the preset potentiometers which give the bias to the gate of the MOSFETs. It is a multi-turn potentiometer. After turning each potentiometer step by step for several turns, I could set the bias voltage on one side as 3.27 volt and on the other side as 3.28 volts, almost equal on both sides. Unfortunately, the meter screen went out of the field during the adjustments, so I am not able to show that here. Anyway, this is at 9 volts and this will not vary even if you give 12 volts because the voltage is coming from IC 7805, which will give only a maximum output of 5 volts. After setting the bias voltages as 3.27 and 3.28 volts, the total current drawn by the board increased to 31 milliampere from the 15.7 which was there earlier, both with a 9-volt battery. Changed over from the tiny 9-volt battery to 12-volt battery from UPS, and it is showing 48.5 milliamperes at 12 volts. That is increased because the voltage is more. After changing over to 12 volts, the bias voltage was again checked, but I don't expect any change as explained earlier. So the bias voltage is seen as 3.27 volts on one side and 3.28 on the other side. There is no change and it is not expected also. I had difficulty in drilling the massive heat sink and several attempts had failed. Many hams advised me to buy WD-40 lubricant and a titanium nitride coated high speed steel drill bits for drilling the aluminum heatsink. That is what I have purchased online and got it. And there is an interesting story about the WD-40. WD-40 has a company by that name as well, and it was earlier named as Rocket Chemical Company, and this WD means water displacement formula 40, and this was the 40th formula which the company had tried in those days long back. WD-40 was originally designed as a coating for the first intercontinental ballistic missile of United States of America. You can see that it drives out moisture, cleans and protects, loosens rusted parts, and the reason why I bought it is my friends told me that when aluminum is being drilled, the debris will stick on to the drill bit and prevent proper drilling. which I also noticed. And this can prevent that by providing a lubrication there. You have to clean intermittently and apply this. These are the titanium nitride coated high speed steel drill bits which I bought online. They look a little bit elegant with a lot of sizes. Maybe I'll have to start with the 2mm bit. That is what my friends who have recently homebrewed the VU2EVQ linear amplifier told me. With new tools in my armamentarium, with renewed confidence, drilling process started. Initially, the heatsink was fixed on a board with nails as advised by VU2EVQ. As many of my friends have suggested, initially a punch hole with a nail and hammer was made to prevent the drill bit from slipping and moving all around the heatsink, which had happened previously several times. Clean the surface with a cloth and sprayed WD-40 every now and then to prevent aluminium debris from sticking to the drill bit. Initial attempt, as has been advised by VU2EVQ and many others, was using a 2mm drill bit, that is titanium nitride coated high speed steel drill bit. Made slow progress without the hole moving all around as in previous attempts. This was the drill bit seen in profile fixed on the drill, that is a titanium nitride coated high speed steel drill bit. Had to use 3 bits from 2mm to 3mm sequentially. Projecting fragments were removed by slowly running the drill over it along the surface to scrape them off and make surface smooth. Otherwise, when screwing the MOSFET, it can damage the MOSFET, these fragments. The hole made was tested with the indented screw to see that it can move inside and outside freely. Then I tested screwing in a MOSFET which was removed during an earlier attempt because there was short in the board. I have used the heatsink compound as well as the insulator sheet. Then heatsink compound was applied on the insulating sheet and placed over the actual board. Heatsink paste was applied on the reverse side of the insulating sheet as well. Then screw was fixed on one side, taking care not to damage the MOSFET. To make a long story short, same process was repeated on this other side for drilling the other heatsink, and it was also fixed behind the MOSFET. This is the current status after fitting the 2 large heat sinks under the MOSFETs. You can see the huge fins, and this is needed because when the MOSFETs run at about 100 watts, a lot of heat will be generated. Now the process is far from complete. I'll have to test the board again for any shorts. Then I'll have to connect the input, RF output, fix everything inside a box, and then go for the final on-air testing. It will take some more time. I hope I'll be able to succeed in the whole process.